Welcome. Welcome to the International Internship University, IIU. I'm thrilled to be your trainer and resources person for today's session on the game as a didactic tool for teaching of mathematics. I am Esposito, Country Director IIU from Italy. This session is a golden opportunity for educators, counselors, parents and students alike. I am IIU Country Director Italy and IIU Web Country Director Italy. I've been teaching mathematics in high school, IT Medi in San Giorgio a Cremano, Naples, in Italy, for 28 years. After graduating in 1994, I am interested in different and various projects, including e-twinning projects that allow twinning between different European schools. I am near-poded certified educator, verified educator on Kaut Academy, and a puzzle coach and trainer, and a Wakelet community leader, book creator, verified author. I work a lot with coding and gamification. I spoke in different international conferences. I am an international speaker and on board of various international organizations. I write texts for math videos for eduboom.it, and I write for a website about great mathematicians and maths anecdotes. I am also a collaborator for math videos for EduPuzzle. Thanks to the visionary Miss Payush Pandit and IIU, we are here to equip you with the skills and knowledge that will truly empower you. Our goal is to ensure that no one is deprived of education and skills, fostering a world filled with capable individuals. Today, we are diving into a captivating presentation that will help us to understand mathematics using gamification. So get ready to embark on a transformative learning journey. So without further ado, let's kickstart today's session and explore the fascinating world of mathematics. Get ready to enrich your skills and broaden your horizons. Thanks to visionary Ms. Payush Pandit and IIU will begin this session. Let's begin and let's share my presentation. Okay. The game as a didactic tool for teaching of mathematics. First of all, being an educator, it's not a way to live, but a way to life. The game to discover a new mathematics. Raymond Smullyan narrates in the introduction to the book Woman or Tiger. My son, the speaker is a friend of Smullyan's, is reading your book and he likes it very much. But when you talk to him, don't tell him he's doing math, because he hates math. If he were to figure out that this is actually mathematics, he would immediately stop reading the book. The author then goes on to claim that he had met a great many people who claimed to hate mathematics, and yet who were enormously interested in any logical or mathematical problem he proposed, as long as it was presented in the form of a riddle, even wondering what would happen if Euclid's elements had been written in the form of riddles. Why this is a priori repulsion for mathematics? Why is this discipline something useless and far from everyday life? One of the aspects that seems to make learning and understanding mathematics difficult is a language that does not admit ambiguity, but above all, that appears far from the common one and from the reality that surrounds us, cold, dry, and abstract. The mathematical game partially recovers this distance between mathematics and reality, since it also uses the so-called extra mathematical language. In this way, the game extends the field of interest and the vocabulary of mathematics, inserting alongside the numbers and letters, often also from other alphabets, objects, animals, anecdotes, and paradoxes, building a bridge between the rigorously theoretical and formal aspects and the concrete areas of application. The first question we want to ask ourselves is, what is the main task of teaching mathematics to pre-adolescent and adolescent pupils? Unfortunately, in common feeling, mathematics is reduced to a set of symbols and concepts in their own right detached from the concrete context. This enormous prejudice is responsible for the widespread distrust of mathematics, often experienced as a boring, frustrating discipline and difficult for many kids. It is throughout a subject in which only numbers and figures are studied, of which the area or volume is calculated throughout pre-packaged receipts to memorize. Sometimes, when it's better, we experience it as a set of games, completely missing the deep, complex value and also the beautiful mathematics and its importance in our society. Nothing we have achieved throughout technological progress would ever been possible without the extraordinary advance of mathematics in the 18th and 19th centuries, which gave us differential calculus, which then allowed physics and other applied sciences to make the first revolution industrial. Even if awareness of the historical importance of this subject and of its studies were reached, and its affection would immediately follow for most students due to the erroneous perception that it is a dead end, which in the era of the Industrial Revolution 4.0, math is useless. In an article of April 14, 2000, Emmer wonders precisely this, namely, whether mathematics is still needed in the age of computers. However, it is essential to understand that today unacceptable education and training are no longer conceivable if they do not involve an increasingly larger part of mathematics, not necessarily aimed at training mathematics professionals, but people with a critical sense capable, independently from the chosen specialization, to know how to rigorously and correctly use the mathematical tools learned. Even men of letters, grammarians, linguists, historians, quantitative history, geographers, climate change, sociologists, experimental sociology, economists, econometrics, need to know how to handle the mathematical tool very well and reason mathematically in order to be able to carry out a type of intellectual activity, characteristics of mathematics. More generally, as the famous French pedagogue Meillet affirms, a good preparation for life cannot be achieved without recourse to a serious mathematical training. A mathematical education gives the individual a conceptual enrichment that no other discipline can give him. The concept of number, that of operation, of mathematical truth, of ration and of proportionality, are part of the mental equipment of modern man. Similarly, a mathematical education accustoms students to go beyond concrete reality to express it in a new, purified, and more abstract language, capable of making evident the similarities between situations that are apparently very distant from each other. So, studying mathematics correctly means learning to reason and to become aware of one's own reasoning. Therefore, students must not only be asked to acquire the habits of correct reasoning, but students must be encouraged to become aware of their own thought processes. The formation of a logical thought is the highest manifestation of human capabilities. Forming it and developing it is a duty of teachers of all levels, regardless of their humanistic or scientific background. Going beyond the sterile contrasts that have so damaged the disciplines of one of the another front in the past. In the primary school mathematics programs where we read, mathematics education contributes to the formation of thought in its various aspects: intuition, imagination, planning, hypothesis and deduction, control and therefore verification or denial. It tends to specifically develop concepts, methods and attitudes useful for producing the ability to order, quantify and measure facts and phenomena of reality, and for forming the skills necessary to critically interpret it and to consciously intervene on it. Choose the formation of a positive attitude towards mathematics will be encouraged, understood both as a valid instrument of knowledge and critical interpretation of reality and as a fascinating activity of human tools. Choose mathematics is affirmed as a symbolic language encoding of abstract models to favor mental processes and the logical construction of reasoning. The math games. Mathematical games, for example, problems created and proposed to groups and all classes of children, respond to the need to strengthen those mental abilities responsible for the acquisition of modeling processes and the application of mathematical skills in order to represent and control reality. Some might be surprised by the statement that mathematics enhances intuition and imagination, especially those students who have had only superficial contact with the study of mathematics, such as memorizing definitions and acquiring pre-packaged techniques. However, nothing is farther from reality, and it is precisely the task of mathematical games to make children aware of this crucial fact as well. Anyone who has undertaken and has already reached a good point in this learning path knows well how intuition is the essential starting point for the abstraction or modeling of problems, from the most concrete to the most abstract. The student's personal challenge is to be able to put himself to the test and solve this type of problem, which is more demanding and difficult than what is commonly proposed in class. The teacher's challenge, equally important and crucial, is to conceive and propose problems that are able to stimulate these abilities. In fact, it is not productive to adopt an attitude of irrational creativity. As the great mathematician Polya tells us, a fool can ask more questions than 9 wise men can solve. And on the other hand, Polya himself, in another passage, reports the sensation of euphoria that every teacher would like his students to experience at last once during the correct resolution of a problem, perhaps simple but significant, where the students, they must go beyond the pre-packaged formula and throughout mathematical reasoning, arrive at a non-obviously solution to the proposed question. A great discovery solves a great problem, but in the solution of any problem, there is a dash of discovery. Your problem may be small, but if it piques your curiosity, engages your inventiveness, and solves it with your own means, you can experience the tension and rejoice in the triumph of discovery. More recently, however, the mathematicians Edward Frenkel commented on the way mathematics is taught in schools in an interview in response to questions. What's wrong with the way most of us are introduced to mathematics? And Frenkel replies, the way math is taught is similar to an art class, where students are told how to paint a fence, but are never shown the paintings of the great masters. When math is incorporated into a discourse later in life, most people shake their heads and say, I wasn't good at math. What they are really saying is, I wasn't good at painting the fence. Problem solving and play are approaches that are capable of revealing a face of mathematics that remains hidden behind the abstract aspect of a discipline. There is another mathematics, one that exerts a fascination capable of enrolling the study of a discipline generally considered difficult and boring. It is therefore of fundamental importance to teach mathematics which takes into consideration the history of these subjects and which puts students in contact with the context in which the author came to discover a theorem or a formula. Teaching of this kind stimulates deductive ability in students, but also imagination and intuition. The game to find stimuli and motivation, a fundamental aspect connected to problem solving and above all to play, is the ability to regain motivation to study mathematics by making these subjects interesting for everyone, even for those who do not consider themselves capable of understanding them. Surprise, paradox, or unexpected results are simulated elements for cognitive activity. They are a bit of a sleight of hand whose trick we are looking for. When a pupil solves a problem or a game, he becomes a protagonist, as inventor or discoverer of the solution. He is no longer being a passive subject positively affects his attention, the quality of learning, and his motivation. The teacher who entrusts the resolution of a problem or a game to his pupils actually gives them a responsibility. The person in charge of the process is the pupil himself. In fact, the main characteristics of problem solving and of the game is precisely the lack of a defined algorithm or a pattern of behavior. In this case, the aim is to find not so much the solution. In this case, but the solution procedure, which must then be formalized at a later time. However, a situation of this kind can cause the student to find himself almost disoriented by so much freedom of action. Often the classic frontal lesson or a demonstration to learn are more reassuring. In reality, all of this depends on the cognitive style that each individual student has. Some prefer discovery, being able to range and discover new things, while others are constantly looking for a predefined pattern that they limit themselves to shy following. In this context, the figure of the teacher assumes a fundamental role, who must try to prepare the students to face different situations, while respecting as much as possible the nature of the individual student. Formal learning and informal learning. Nowadays, there is a tendency to distinguish scholastic learning from non-scholastic learning in a very clear way. Everything that is not learned at the school has begun to be defined as informal. And by contrast, the word formal is becoming increasingly synonymous with the scholastic. In particular, Pietro Cerreta distinguishes them by listing a series of properties. Informal is voluntary, non-assessed, and non-certified and extracurricular, while formal is seen as compulsory, assessed, and certified, scheduled. Informal learning includes all those initiatives, such as science museums, game exhibitions, mathematics festivals, and many others that are so dear to me precisely because of their highly informative content. Honestly, however, I don't think one of the two methodologies can be said to be better than the other, but I think it is important that a boy or a girl can acquire his or her personal baggage throughout both types of training. Formal learning may seem rigid and obsolete, but it is fundamental for clear, complete knowledge, which then serves as a basis for building new knowledge, skills, and abilities. On the other hand, informal learning, which appears dispersive, incomplete, and confusing, very often succeeds where the classical structure fails, because it has the ability to arouse curiosity and passion by making the boy and the girl feel the author of his or her own learning, a learning that becomes active and no longer passive. The question that arises then is the school capable of informal learning? If so, how? The answer to the first question is definitively yes, as I have experienced it several times. As far as the second question is concerned, I believe that games and problem solving can be among the most valid tools for this purpose, at least in teaching mathematics. Playing problem solving in teaching. All the discourse made so far can therefore be summed up in saying that the school can no longer be the standard bearer only of formal learning, but must become the expression of an overcoming of these distinctions by carrying out initiatives that have informal learning as their objective, and above all, more difficult, developing the ability to synthesize all the experiences that the students have, aiming to train people at 360 degrees. Teaching looks at the game and the problem solving essentially from 2 points of view. First, the problem as a means, using the problem to arrive at knowledge by implementing a problem-based teaching, from time to time critical problematic situations, even in the form of a game from which ideas can arise. In this case, the problem solving is a means, a methodological tool to be used to pursue educational objectives. Second, the problem as a goal, a teaching that develops the aptitude for problem solving in the students. Problem solving thus becomes an end that it is itself the objective of the didactic intervention. In relation to this, both learning to apply and adapt solution strategies to different problems and monitoring the process used in solving a problem and reflecting on it acquires particular importance. Game and problem solving as a method. The problem and the game can be used as a source from which to generate ideas, to introduce theoretical concepts. It is a question of posing a question from which a conjecture can arise, rather than following the traditional top-down didactic order, typical of demonstrations, which leaves the way in which concepts are born in the shadows. One can start from the bottom, from a problematic case, gradually going back to a rigorous idea. In this way, implements a constructive approach to learning mathematics. The bottom-up path is that of analysis and is the path that is typically followed when looking for the solution to a problem. Once the steps of this path have been defined, it can be codified or executed top-down synthesis. The method of analysis is important from an educational point of view, as it develops logic and problem-solving skills, More than a knowledge, it is a know-how and radically different from way of proceeding and reasoning. There are also other aspects for which play and problem solving constitute a teaching resource. First, the positive function of the error. Solving a problem allows the student to profit more from the mistakes made, as he is curious to find out what went wrong in his reasoning. What moves him is a challenge he had launched to himself in seeking the solution. Second, the possibility of intervening on the spontaneous models of the students. Problems and games can be used to bring out students' spontaneous models. That is, they can be structured in such a way as to highlight and at the same time challenge the various misconceptions in order to be able to intervene on them. And third, the opportunity to stimulate interest in mathematical thinking. As already mentioned above, questions of historical, philosophical, and etc. interest can also be presented in the form of a game. One of the most famous examples is undoubtedly that of the Tower of Hanoi and the principle of induction. So problem solving is a goal. Problem solving is a skill in its own right and as such can be acquired with the practice. It is therefore necessary to observe and imitate how other people succeed. But you learn to solve problems above all by solving them. The approach to a problem can be of a various nature: intuitive, systematic, algorithmic, partial by trial and error, by exclusion, etc. Each student may respond better to one approach than to another. And when considering a specific problem, some methods are better than others. However, it is important that students know the various alternatives so that faced with a problem, they have a certain flexibility, which allows them to choose the most suitable tool to use. This flexibility of approach also proves to be very useful in certain cases, when during the resolution of a problem, it may be necessary to change one's point of view, and one realizes that the road taken initially is not leading us to the solution. This multi-approach vision to games and problems favors the use and development of different and complementary characteristics such as intuition and planning, in clear contrast to the logical tradition of the predefined algorithm and receive. At a didactic level, therefore, it is important to help pupils to know and know how to use as many types of approaches as possible, without failing to value the specific characteristics of individuals. Starting therefore from the assumption that the objectives of proposing a problem are principally two. First, help the student to solve the proposed problem, and secondly, develop the student's abilities so that he is able to solve the problems he will have to face later. It becomes spontaneous to wonder how much and how a teacher should suggest solution methods to students. In fact, on the one hand, the student left alone in front of a problem could get stuck and not make progress. On the other hand, if the teacher is too generous with the suggestions, the student could not develop any skills. The teacher, therefore, should intervene in the right measure and help the boy or the girl students in an appropriate way, providing them with the necessary input to proceed independently in the search for the solution, making sure that they learn to ask themselves the right questions, the problems they will face later. A possible scheme of guiding questions to provide the necessary help is the one proposed by George Polya in How to Solve Math Problems. He said, to properly group the questions and suggestions of our scheme, we will distinguish 4 phases in the development of the work. First, you must understand the problem. You need to clearly know what is required. Second, you have to discover the links that intercede between the various information, between what you are looking for and the data to understand the type of resolution, and compile a convenient plan. Third, we proceed to the development of the plan. Fourth, it is necessary to carefully examine the result obtained and proceed to verify and discuss it. The questions indicated by Polya follow these classifications in stages. First, understanding the problem. What is the data? What is the unknown? Is there superfluous data? Is there hidden data? Is the condition sufficient to determine the unknown? Is not sufficient? Is it overabundant? Is it contradictory? Second, compiling a plan. Is this a no issue? Has it already presented itself in a different guise? Is there a known problem associated with this? Do you know a theorem that could be useful? Can it be exploited? Have all the data been used? Is it possible to identify auxiliary problems necessary for the solution of the problems? Can the problem be broken down into sub-problems? Third, developing the plan. As you develop the plan, verify each step slowly and with attention. Can you prove its accuracy? Fourth, verification of the plan. Can the result be verified? Is it possible to get the result in another way? Can you see it at a glance? The proposed list of questions is not only useful for solving the problem, but also for reflecting on the possibility of exploiting known procedures, possibly adapting them to the proposal problem, and for monitoring the solution process by reflecting on it. To develop problem-solving skills, in fact, it is necessary not only to try to find solutions to problems, but to investigate and explain the reasons that lead to the choice of the strategy used. And let's speak about intuition and deduction. It is also important, in my opinion, to emphasize the importance of the balance between the various methods that a teacher can use, especially between intuition and deduction. On the one hand, there are imagination and the idea, and on the logical rigor and formalization are different, but both are fundamental. Formalization does not kill intuition, but expresses it, as Professor Alessandro Benedetti said. It is therefore essential that a professor transmit to the students, in addition to the methods for tackling a problem, the tools necessary to formalize it. If in the first phase it may be important to work with the extra mathematical language and let free rein to ideas, subsequently it becomes essential to transmit a demand rigor, as there is a risk that the student, while proceeding correctly, does not bother to explain in terms precise the reasoning that follow it, considering the fact that most of the time it is not said that he is able to do it. Instead, it is necessary that the children learn to use mathematical language and its model to express themselves. For example, in the case of a theorem, the student must explain the hypothesis and the thesis. Then he must be able to explain the sequence of steps or logical deductions which, starting from the hypothesis, lead to the thesis. And in the event of a problem, For example, the student must be able to identify and correctly express the data, possibly eliminating superfluous ones, and must then identify and explain the unknown or unknowns and the relative limitations. At this point, the sequence of mathematical steps leading to the solution must be explained. In both cases, it is good that the pupils also know how to explain the method used. For example, a proof that can be by contradiction, direct, etc. A problem can be tackled with a top-down, bottom-up, etc. technique, depending on the situation. Students can also be led towards greater formalization by making them elaborate a synthesis process that leads from the solution of the problem to the model according to the following steps: identification of the proposed, data symbolization, identification and explanation of the initial state, identification and explanation of the final state, identification and explanation of constraints, possible states and impossible states, identification of the transformation operators that allow me to pass from one state to another, explanation of sequence of operator states that leads from the initial state to the final one, and possible search for the optimal solution. To train the students to carry out these self-monitoring operations, it is advisable for the teacher solving a problem in class to ask himself aloud the same questions he asks the students, explains all the steps of reasoning, and to be the one to guide them gradually develop the specific language and the capacity for formalization. Let's not forget that Archimedes intuited his result not by immersing himself in the bathroom, but throughout a formalized method, even if not acceptable at the time as valid. Once he found the result, he formalized it and demonstrated it using the deductive reasoning typical of demonstrations. Solving a problem requires all three phases of the great mathematician, and we cannot accept to stop at the first one just because it made us guess the result. I can conclude that a different teaching of mathematics is possible. It is a teaching that uses play and problem solving as tools and as didactic purposes, which manages to alternate moments of formal learning with those of informal learning in the students, making a synthesis between the different experiences and the different methods. I believe in the development of a teaching method that starts from the student's previous knowledge, based above all on the dialogue of the lesson, and which always seeks active learning on the part of the students. A teaching method that knows how to develop reasoning and imagination in the children to ensure that when faced with a problem, they have analytical skills, intuition, and know how to formalize and summarize the results using the specific language of the subject. Emotional involvement plays a fundamental role in the path of growth and development, and playful activities are, by definition, implied involvement. Learning takes place according to a path of discovery that implies active and all-encompassing participation. For this reason, play plays a fundamental and irreplaceable role within the learning process. It not only stimulates cognitive thinking, but leaves important traces on an emotional, affective, and relational level. The game is always active involvement. It is a sociability and collaboration. It is a attention towards the achievement of objectives and strategic research. Game is a recognition of diversity. It is active collaboration with a plurality of points of view. It is a collective construction, and as such, never reproductive. Game is a pleasure, not anxiety. And by playing, you learn. Attention is then focused on the dynamics of the game, not on the disciplinary contents. and the search for solutions continuously stimulates inventiveness, imagination, creativity, and divergent thinking. So I want to conclude my speech with a quote that a woman, an educator, and pedagogist, an Italian pedagogist, very famous all over the world. She is Maria Montessori, and she said, "To teach, you need to excite." However, many still think that if you have fun, you don't learn. It's not so. So I want to thank you from the bottom of my heart, Ms. Pariush Pandit and IIU for the opportunity given to me to be a trainer this afternoon and to be able to share my maths knowledge with all of you. I thank you for listening to me, and I wait for you for next sessions about mathematics and games. Thank you again.